Hi, this is Thomas. Welcome to math class. We're continuing to work with differential calculus, and today we're looking at a calculus application concept known as optimization. There are various outputs we might want to maximize, such as profit or volume of a container. Other outputs we might want to minimize, such as expenses. And what we want to do is evaluate our inputs so that we can maximize, or in some cases minimize, our output. The way we're going to do the optimization is by considering the zeros of the derivative of whatever our function is. When I look at my zeros we've seen in stationary points, that when I look at zeros on a sign diagram, I might determine that the points to the left of a zero are negative, and the points to the right of a zero are positive, and the points farther right, the points to the right of the next zero, are negative. And I know what I have is going from negative to positive, I have a local minimum, and then going from positive to negative, I have a local maximum. And if I'm evaluating, say I'm evaluating a function relating to costs, I would like to know how to minimize costs, and by identifying a local minimum, I can then determine the best input to result in minimal costs. Or if, in the example we're looking at, we'll look at maximizing profit, I'll want to know which output gives me the maximum point, and that will be the input that I want to use for maximizing my profit. So let's look at that example. So we're going to look at the example of profit maximization. And we have a cost function and we have a revenue function. Our cost function, this is a formula, as well as the revenue function. These would be formulas generated by engineers at a company. In our context, we'll be given these functions. The cost function is 720 plus 4x plus 0.02 x to the power of 2 dollars. And for a given input, for a given number of units produced, I'll have an output of the total costs associated with that number of units. Now, I'm not focused on minimizing costs, rather I'm focused on maximizing profit. I could, in another analysis, simply focus on minimizing costs, but here I want to look at, and as will be the case most times I'm evaluating a company's economic performance, I want to consider the net result, which will also include revenue from my customers. My revenue function is 15 minus 0.002x dollars per unit. And what I want to do is I want to combine these two into one function, and then I'll proceed from there. First observation is one of the functions is total dollars, that's the cost function, and the second function is dollars per unit. That's our revenue function. So I'll update the name of the revenue function to R of x. Since I have the revenue function for 1 unit, what I will do is I will create a new function, which is the profit function, and that's going to be all revenue, which is 15 minus 0.002x, all multiplied by x. X is the number of units that I'm going to produce, and in the function for revenue there is an x, but the output of that function is dollars per unit of revenue. I want total dollars per unit. So that entire function I need to multiply by x. X is going to be the number of units that I will produce, minus my costs. and I have the total cost function. So I will subtract 720 plus 4x plus 0.02x squared from the total revenue function to get to the total profit function. Now I will expand the first half of this function to 15x minus 0.002x to the power of 2. And distribute the negative 1 to the second half of the function, minus 720 minus 4x minus 0.02x squared. Then I can simplify to negative 0.022x squared plus 11x minus 720. So this is my profit function, total profit. What I want to do is determine the input, the x value, number of units of production, to maximize the output, which is total profit. In evaluating optimization problems, I want to go through a consistent process, 6 steps. My first step is diagram. And in this case, what I see is I have a quadratic equation. The coefficient of x squared is negative, so this is opening down. And I see that I have a y-intercept of negative 720. So I'll sketch my parabola. And what this allows me to do is visualize what it is that I'm looking for. I'm looking for the highest point of the parabola. So there is a particular x that I want to calculate. I'm going to take the derivative of my function to do that. That will result in the maximum possible y for this function. In other words, the input of units produced to maximize the output of profit to the company. For this function, a helpful diagram was the actual graph of the function. But often, and probably in most cases, what you'll find is that your diagramming will be a representation of whatever project you're working on. If you're trying to maximize the volume of a cube or maximize some measurement of a building, then diagramming the cube or the building will be your step 1 diagram. Step 2 is a formula. And we've actually calculated our formula. In our case, we've done that. 2 important points regarding formula. One variable in some situations, as in ours, we're only working with one variable from the beginning. If you find that you have 2 variables, then you need to look for a second relationship and use substitution to eliminate the second variable, so you're only working with one variable in your function. We also want to be sure to identify restrictions. In our case, that will be the restriction x is greater than 0. Let's consider the possibility of 0. If we have a money-losing operation, there is a possibility that we just don't want to make anything. There is no possibility for profit, and therefore maximizing production at 0 would have profit of 0. That might be the highest profit possible. But we can't manufacture a negative number of units. So our restriction is that x is greater than or equal to 0. Third step is first derivative zeros. So looking at our function, the derivative of negative 0.022x squared, that's the first term, is 2 times the coefficient, so negative 0.044x to the power of 2 minus 1, plus 11x becomes plus 11, and minus 720 is 0, so we leave that off. Now I want to calculate the zeros for the derivative. 0 equals negative 0.044x plus 11. So I'll add 0.044x to both sides and end up with 0.044x equals 11. Then divide both sides by 0.044. And my x value is 250. In this case, we have only one solution. In other scenarios, there could be more than one solution. We want to evaluate the solution in this case, or multiple solutions, against the restriction that we identified. X is greater than or equal to 0. X equals 250 does meet that restriction. We do have a value greater than or equal to 0. Next step, step 4, is sign diagram. And I want to evaluate all of my solutions. Again, in this example, we only have one solution, but we evaluate all solutions to determine what kind of zero, what kind of stationary point we have in the original function. So I'm going to evaluate 250, looking at a point less than 250 and at a point more than 250, what will the output of the derivative be? So we can use the values of 0, and we can use the value of 1,000, because these will give me round numbers that are easy for me to evaluate without doing any calculations in the calculator. So looking at my derivative, if I input 0 for x, I have negative 0.044 times 0 is 0, plus 11 will give me a positive value. Now moving to the right of 250, let's test 1,000. Negative 0.044x times 1,000 is 44, negative 44. Plus 11, negative 44 plus 11, is a negative value. And so what I see happening at the point 250, the input value, x value of 250, is the original function is going up, and then it begins to go down. So this is a local max, and that's what I'm expecting, that's what I need. I want a max point, an input value that will maximize my output, and now I've identified that input, 250 units. Now my fifth step is identify solution. And first I begin by evaluating the derivative zeros. In our case, we only have one, 250. But if we had derived 2 or more zeros, we would evaluate all zeros with the sign diagram, and we might find that we have one local maximum and one local minimum. So identifying the solution would be understanding that we need a maximum and selecting the maximum and eliminating the minimum. Again, in this case, we only have one solution, but in cases in which there are more than one solution, you need to be sure you know what you're looking for, either a maximum or a minimum, and select accordingly. We also need to consider, in some cases, endpoints. That doesn't apply in our scenario. Looking at our diagram, we see that the shape of the function is a downward opening parabola, so there's only going to be one maximum. The local maximum is the absolute maximum on the entire curve. For other functions such as cubics, which have more than one change of direction, you might need to consider additional x values as possible maximum or minimum points. And finally, step 6, state the solution. And we were looking for the production level to maximize profit. So that production level is 250 units. So this concludes our video on optimization. Thanks for watching, and I'll see you in the next lesson.